Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 asks, is BCl3 polar or nonpolar? So this is boron trichloride. Okay, so to find out whether or not a molecule is polar or nonpolar, we need to first draw out its Lewis structure. So when drawing out a Lewis structure, we need to calculate the total number of valence electrons for this molecule. So boron has 3 valence electrons, and chlorine has 7. And since there are 3 chlorine atoms in this molecule, we multiply this by 3 to give us a total of 24 valence electrons. So now we can start by drawing out the skeletal structure for this compound. And our central atom will be the boron, since it is less electronegative than the chlorine. And now I can draw 3 single bonds to the chlorine atoms, like so, and draw in all of their lone pairs. So if I count out how many electrons I've drawn so far, each bond contains 2 bonding electrons, and each of the chlorines contains 6 non-bonding electrons. So in total, I have my 24 valence electrons already drawn. Now we can analyze our structure and see the type of structure by using a helpful VSEPR chart. I'm just going to look up a VSEPR table that'll tell us the type of molecular shape we have for this molecule. So if we look at our boron, boron has 0 lone pairs, and it also has 3 bonded atoms. So using the VSEPR theory table, this tells us that when we have 0 lone pairs and 3 bonded atoms, we have a trigonal planar molecular shape and electron geometry. And all of the bond angles are 120 degrees. Okay, so let's also recall that chlorine is much more electronegative than the boron, so each of these chlorine atoms will have dipole moments pointing in the direction of these chlorines. But if we look at our trigonal planar structure, you'll see that it is symmetrical. So I'm just going to write down here, we have a symmetrical structure. And all of these dipole moments cancel each other out. So we can also say that this molecule has a 0 net dipole moment. So because of this, BCl3 is a nonpolar molecule. Even though a boron-chlorine bond is polar. I'm just going to write up here, the boron-chlorine bond is a polar bond because of their electronegativity difference value. It's greater than 0.4 but less than 1.69. And the junior tutor said that boron trichloride is a nonpolar molecule. The 3 boron-chlorine bonds, even with dipole moments, are arranged in trigonal planar, which negates the individual dipole moments. Yep. So this solution is correct. Okay, so question number 2. Is phosphorus trichloride polar or nonpolar? Follow the steps below to determine if the molecule is polar or nonpolar. So first, let's sketch out its Lewis structure so that we can visualize what this molecule may look like. So when writing out the Lewis structure, we first need to find out the total number of valence electrons for this compound. So phosphorus has 5 valence electrons and chlorine has 7. And since there are 3 chlorine atoms, we multiply this by 3, which gives us a total of 26 valence electrons. So now let's try to draw out the skeletal structure. We'll have phosphorus as our central atom, and then 3 single bonds to the chlorines. And I can also draw in all of the lone pairs on each chlorine atom as well, like so. And if we recall that each bond contains 2 bonding electrons, and we have 3 bonds, plus each chlorine atom has 6 non-bonding electrons. If we count out all the electrons I've drawn so far, I only have 24 out of the 26. So for the remaining 2, I'll put as a lone pair on the phosphorus. So now we have our final Lewis structure for phosphorus trichloride. So now we can follow the steps that they give us in the question. So step 1, the phosphorus chlorine bonds are blank. So I think they mean to ask, are they polar or nonpolar? So to find out the polarity of these bonds, we need to look at the electronegativity difference between phosphorus and chlorine. So let me look up electronegativity values for these elements. So we'll use this one here. Chlorine has an electronegativity value of 3, and phosphorus is 2.1. So the electronegativity difference between the two is 0.9. So therefore, the phosphorus-chlorine bond is polar, and we know that because its electronegativity difference is greater than 0.4, but it's less than 1.69. So that answers step A. Step 2 wants us to look at the molecular geometry of this molecule. So by looking at our phosphorus atom, we can see that it contains 1 lone pair and 3 bonded atoms. So if we look at a VSEPR chart, we can find out its molecular shape and electron geometry. So when we have 1 lone pair and 3 bonded atoms, we have a trigonal pyramid molecular shape. Trigonal pyramid molecular shape. And a tetrahedral electron geometry. So now I know the electronegativity difference between phosphorus and chlorine, and I also know the molecular shape. So if I were to draw dipole moments going towards the chlorine atoms like this, notice that they don't cancel each other out because of the lone pair on the phosphorus. So we have a net dipole moment, kind of like this, and we can say that we have a non-zero net dipole moment. And because of this, our molecule is polar. And this is due to the polar bonds plus its molecular shape. Okay, so the junior tutor said that to determine the polarity of a molecule, we need to first write its correct Lewis structure and molecular geometry. So they kind of summed up how we would do that. They got 26 valence electrons and drew the correct Lewis structure. And they didn't show the calculation of the electronegativity difference, but they already knew that it would be polar. They found that the Vesper shape looks more like this, and it's trigonal pyramid. So the molecule is polar because the bond dipole is occupied only in one direction, from the phosphorus atom to the lone pair, and lone pair to the chlorine atoms. Yep. So this solution is correct. Question number 3 is, what is the Lewis structure for N2, which is diatomic nitrogen? So to write out the Lewis structure, we need to find out the total number of valence electrons. So a nitrogen atom has 5 valence electrons, and we have 2 nitrogen atoms, so we multiply this by 2. So we have a total of 10 valence electrons. So since we only have the 2 atoms, we can draw first showing the single bond, and we know we need to have 10 electrons in total in our final structure. So if we formed a triple bond between the two and calculated how many electrons we have so far, each bond contains 2 bonded atoms, and we have 3 bonds, so we only have 6 out of the 10 electrons. So for the remaining 4 electrons, we can equally distribute them between the 2 nitrogen atoms to get the final Lewis structure. So if we look at one of the nitrogens, we'll see that it contains 1 lone pair and only 1 bonded atom. So if we looked at its Vesper shape, when we have 1 lone pair and 1 bonded atom, its molecular shape and electron geometry is linear. Okay, so the junior tutor said that a Lewis dot structure is a representation of an atom, ion, or compound that shows how the valence electrons of the atoms are distributed as bonds, lone pairs, and sometimes radicals. And it may need some trial and error, so they have a step-by-step guide and some rules that'll help us draw out the structure. So they summarized how to do it for diatomic nitrogen. Nitrogen atoms typically create 3 bonds, so they showed the triple bond and the remaining 2 electrons for each nitrogen. They showed how we would calculate for formal charge and got the correct Lewis structure. So this solution is correct. Okay, so question number 4. How many valence electrons does magnesium have? What shell are they found in? Is this shell full? And is the magnesium atom likely to bond with other atoms? Why or why not? Okay, so to answer this question, first let's draw the electron configuration for magnesium. Okay, so the first step in writing electron configurations is to divide our periodic table into different sections. So we can divide it into the s orbital, which is shown in the light blue, including the helium atom here, and the p orbital, which is in green, and the middle transition metals is the d orbital, or the d block, and the last 2 rows, the lactonides and actinides, is the f block. So let's locate magnesium on the periodic table. So it's found here, atomic number 12. And starting from hydrogen, we move left to right across the periodic table, writing the row number, followed by the block letter. And to show how many electrons are in each orbital, we'll use superscripts. So every s orbital is able to hold a max of 2 electrons, and the p orbital holds a max of 6. Okay, so let's start to write the electron configuration. Starting from hydrogen, we write 1s2, and then 2s2, and then moving across to the p block, we write 2p6, and then we found magnesium here, so we just need to write 3s and then 2. So we can see here that there should be 12 electrons in total, which there are. And the question asks, how many valence electrons does magnesium have? Okay, so the 2 valence electrons are in shell 3. So we can say that therefore there are 2 valence electrons. They are found in the 3s shell. And is the shell full? The shell is full. Since an s orbital can hold a max of 3 electrons. Or 2 electrons, sorry. And then the last part asks, is the magnesium atom likely to bond with other atoms? Why or why not? Okay, so yes. Magnesium is able to bond with other atoms. And the reason for it is because its two valence electrons are likely to be donated to form ionic bonds. So for example, we can have magnesium bonding with two chlorine atoms to form magnesium chloride. We can have magnesium bonding with a single oxygen atom to form magnesium oxide, and so on, so forth. So the junior tutor said that magnesium belongs to the S block of the periodic table, or the two groups in the leftmost part of the periodic table. Belongs to the third row, which indicates the energy level of its outermost shell, or the valence shell of the atom. Since magnesium is in the second column of the S block, thus it has two valence shells in the 3s shell. An orbital can hold a max of 2 electrons, and since an s orbital only has one shell, this means that the shell is full. Magnesium can bond especially with polyatomic ions, but for the halogens and the anions in a salt compound in a solution, it usually just gives off its 2 electrons to the anion, since it will be more stable giving off its 2 remaining electrons than completing the 8 for the octet. Yep, so this solution is correct. Typical compounds formed with magnesium can be magnesium chloride or magnesium oxide, just to give some examples. So it doesn't need to bond with polyatomic ions, especially because sometimes it can form these simple binary compounds as well. Okay, so question number 5 is CH3OH polar or nonpolar? So this is also known as methanol. And we can sketch out the Lewis structure of methanol as well, just to see whether or not it's polar or nonpolar. So to draw out its Lewis structure, we first need the total number of valence electrons. So for carbon, there's 4 valence electrons. For hydrogen, there's only 1. We multiply this by 4. And for oxygen, there are 6. So this gives us a total of 14 valence electrons. So now we can try to draw the skeletal structure. So the carbon will be bonded to the 3 hydrogens, and another bond to the oxygen, and the oxygen can be bonded to the last hydrogen. So each bond contains 2 bonding electrons, and we have a total of 5 bonds drawn in the structure, so we have 10 out of the 14 electrons. So for the remaining 4, I'll place them as lone pairs on my oxygen, since oxygen didn't have a full octet yet. So now I have the Lewis structure for methanol, and we first need to look at the electronegativity values for carbon, oxygen, and hydrogen. So let me write all of the electronegativity values here. And this will help us determine whether or not any of the bonds are polar or nonpolar. So let's look at different electronegativity values for these atoms. Okay, so carbon has an electronegativity value of 2.5, hydrogen's is 2.1, and oxygen's is 3.5. So I'll just write here that we have a polar bond when the electronegativity difference is greater than 0.4 but less than 1.69. And we know we have a nonpolar bond when the electronegativity difference is less than 0.4 or equal to. Okay, so now let's calculate the different electronegativity value differences between our atoms. So first let's look at the carbon-hydrogen bond. Carbon has an electronegativity value of 2.5, hydrogen's is 2.1, so their difference is only 0.4, so therefore this is a nonpolar bond. If we were to look at the carbon-oxygen bond, oxygen's is 3.5 and carbon's is 2.5, so their difference is 1. So therefore this is a polar bond. And we can do the same thing for the oxygen and hydrogen bond. 3.5 minus 2.1 is even more polar. So it's 1.4. So now if we were to write dipole moments in this molecule, we'll have them kind of gearing towards the oxygen like this. So since these dipole moments aren't able to cancel each other out, then we can say that methanol is a polar molecule. So this means it's able to dissolve in water if they were both in solution. Okay, so the junior tutor has a pretty lengthy description, so let me just try to graze through it. Okay, so they describe the difference between polar molecules and nonpolar molecules, and how you can find the electronegativity difference between the two atoms. Okay. They talk about hydrogen chloride, which would be a polar molecule since chlorine is much more negative, electronegative than the hydrogen, and it will lead to unequal sharing of the bonding pair. Okay, so they have some nonpolar molecules examples as well. And because a nonpolar molecule contains a symmetrical structure, the dipole-dipole moment is cancelled out. For the case of methanol, it has a bent structure where it forms an asymmetric structure, hence making the net electric dipole moment's negative end move towards the oxygen atom. Therefore, methanol is a polar molecule. Yep, so this solution is correct. Okay, so question number 6. Draw the Lewis structure for acetone and answer the following. Which, if any, hydrogen atoms in acetone can participate in hydrogen bonding? Which, if any, non-hydrogen atoms in acetone can participate in hydrogen bonding? And is acetone capable of forming hydrogen bonds? If yes, does acetone function as a hydrogen donor or hydrogen acceptor or both? Explain. Okay, so first I'll just show the structure of acetone. So it can also be known as propanone. So this means it is a three-membered or three-carbon long chain. And in the middle, there's a carbonyl group or a ketone. So this is acetone. Okay, so now let's try to answer the different questions. Which, if any, hydrogen atoms in acetone can participate in hydrogen bonding? So if we look at all of the hydrogens in this structure, they're all bonded to the carbon. So in order for hydrogen bonding to take place, these hydrogens need to be bonded to an electronegative atom, such as oxygen. But since they're bonded to the carbon, then that means that no hydrogen atoms in acetone can participate in hydrogen bonding. And this is because carbon is not, or I'll just say that, yeah, carbon is not electronegative enough. And I'll also put that the difference in electronegativity between carbon and hydrogen is only around 0.4, which is pretty low. So for part B, which if any non-hydrogen atoms in acetone can participate in hydrogen bonding? So in fact, oxygen can participate in hydrogen bonding. And the reason for this is because it has a very high electronegativity value. I'll just say due to its high electronegativity. And now they say, is acetone capable of forming hydrogen bonds? If yes, does acetone function as a hydrogen donor, a hydrogen acceptor, or both? Okay, so acetone can be a hydrogen acceptor. Okay, so let me show why. So we mentioned earlier that oxygen is more electronegative compared to the carbon. So because of its electronegativity, a dipole moment can form in the direction of oxygen, making acetone have a partially negative side and a partially positive side. So when acetone is exposed to other polar molecules such as water, so let me draw water here. So similarly, water is a polar molecule, so there's going to be a net dipole moment going towards the oxygen, making this side partially negative and the sides with the hydrogens partially positive. So now that oxygen on the acetone can participate in hydrogen bonding with the hydrogen on another molecule such as water. So then I'll just label this as a hydrogen bond. So this is hydrogen bonding. making the oxygen on acetone a hydrogen acceptor. And for this example, the water acts as the hydrogen donor. So I'll just add that too. Water is the hydrogen donor in this example. Okay, so this kind of sums up hydrogen bonding. So now let's see what the junior tutor said. So they have the correct Lewis structure of acetone, and they said for part A, there are no hydrogen atoms that can participate in the hydrogen bonding because they're not attached to a more electronegative atom in the compound. B, the oxygen can participate in hydrogen bonding because of its high electronegativity. C, acetone functions as a hydrogen acceptor due to the presence of oxygen in the compound. Yep, so this solution is correct. Okay, so moving on to question number 7. How many grams of Fe2O3 are produced from the absorption of 4.85 times 10 to the 3 joules of heat according to the balanced thermochemical equation? Okay, so they balanced it out for us, which is good. And we have 4 moles of iron plus 3 O2 produces 2 iron oxide. And we'll add the delta H value, which is 65.2 kilojoules. Okay, so they also gave us the molar mass of the magnesium oxide, so I'll just add that down here. Okay, so we can answer this question in multi-steps. But first, let's recall that when we have enthalpy, which is the delta H, enthalpy is known as an extensive property. So this means that enthalpy is proportional with the amount of substances in the reaction. So this will help us answer our question because we have a balanced thermochemical equation and we know that enthalpy is proportional with the amount of substances. Then we can solve for the grams of iron oxide that are produced. Okay, so first, we just need to convert the joules that were given. So we know that 4.85 times 10 to the 3 joules of heat were absorbed from this equation. So I'm just going to convert this to kilojoules so that we can compare it to the enthalpy of the balanced equation. So I'll just put 4.85 times 10 to the 3 joules is equal to 4.85 kilojoules. Okay, so now these two values can be related to each other since they are in the same units. Okay, so now step 2. I want to try and figure out the number of moles of iron oxide. So I know that when I have 2 moles of iron oxide that was produced, then 65.25 kilojoules, or 65.2 kilojoules, was absorbed. Oops, needs to be in red. And what we are trying to solve for are the number of moles of Fe2O3 that are produced when 4.85 kilojoules were absorbed. So now we just need to solve for x. So x is equal to 0.1487 moles, and this is of iron oxide. So lastly, we can solve for the grams. So mass is equal to the number of moles times molar mass. So we know our number of moles from the previous step was 0.1487, and the molar mass was given in the question. It was 159.7. Oh, it should be grams per mole. Let me just add that here too. And now you'll see that our moles will cancel out, and we're left with our mass in grams. So you should end up with around 23.8 grams of iron oxide are produced. So this is option number C, or letter C. And the junior tutor said that enthalpy is an extensive property. It means that the value of enthalpy change is proportional with the amount of substances in chemical reactions. Use stoichiometric relationships to calculate the mass of iron 3 oxide produced. So they showed it in just one line. They have the 2 moles of iron 3 oxide are produced when 65.2 kilojoules of heat is absorbed. And we're trying to find the moles of iron oxide produced when 4.85 kilojoules of heat is absorbed. So they solved for x, and they already showed the multiplication step with the molar mass of iron oxide, and they also got 23.8 grams. So this solution is correct. Okay, so question number 8 looks like it's multi-step. Consider the bromate ion BrO3 minus. Draw the complete Lewis structure. Determine the total number of electron groups or clouds surrounding the central atom. Determine the electron geometry of the groups around the central atom. Determine its molecular shape. Determine the molecular polarity, and also determine the attractive force, dipole-dipole, etc. Okay, so we have the bromate ion, which is BrO3 minus. And for part A, when we need to calculate, or when we need to draw the Lewis structure, we first need to find out the total number of valence electrons for this ion. So bromine has 7 valence electrons, and oxygen has 6, and we have 3 oxygen atoms, so we multiply that by 3. And you'll also notice that the ion has a -1 charge. So this means an additional electron needs to be added to our total electron count, and we end up with 26 valence electrons in total. Okay, so now we can start to sketch out the skeletal structure for this ion. So bromine will be our central atom, and then I'll draw 3 single bonds to each of the oxygens, and I'll make 2 of them have a double bond. Since I know these oxygens will be neutral, and the overall ion needs a negative charge, which is why I'm leaving the last oxygen to be single bonded, since it will carry that negative charge. So let's count out how many electrons I've drawn so far. So each bond contains 2 bonded atoms, so we have 10 bonding electrons, and then I'll just count out all the electrons in the lone pairs. So we only have 24 out of the 26 for this ion, so for the remaining 2 electrons, I'm going to place them as lone pairs on our bromine. Okay, so this is the Lewis structure of bromate. And for part B, we need to determine the total number of electron groups or clouds surrounding the central atom. So we have 1 lone pair and 3 bonded atoms. So therefore, we have 4 electron groups, which can also be called charge clouds. Okay, so for part C, we need to determine the electron geometry of the groups around the central atom. So we know the number of charge clouds and the number of lone pairs. So if we use a VSEPR chart, then this will help us answer the remaining questions. So when we have 1 lone pair and 3 bonded atoms, this gives us a trigonal pyramid molecular shape. Okay, so that's for part D. And part C is looking for the electron geometry. So again, using our VSEPR table, we'll see that it is a tetrahedral electron geometry. So I just wrote out the molecular shape first. So we have trigonal pyramid molecular shape and tetrahedral electron geometry. So part E is to determine the molecular polarity. So is it polar or nonpolar? So to do this, let's find out if the bromine-oxygen bond is polar or nonpolar. So to do that, we need to calculate the electronegativity difference between bromine and oxygen. So let's look up their values. So oxygen has an electronegativity value of 3.8, or 3.5, sorry. And bromine has an electronegativity value of 2.8. So the difference between the two is 0.7. So therefore, we have a polar bond. And we know that because when we have a polar bond, this means that the electronegativity difference was greater than 0.4, but less than 1.69. So now that we know that the bromine-oxygen bond is polar, then we can draw dipole moments on our molecule in the direction of the oxygen. And because of the lone pair on the bromine, these dipole moments don't cancel each other out. So therefore, the bromate ion is polar. Since we have a non-zero net dipole moment due to the lone pair that causes an unsymmetrical molecule. Or I'll just say unsymmetrical ion. And there's still a part F, determine the major attractive force, dipole-dipole, etc. So just to sum it up, the dipole-dipole is the main attractive force. Because of that electronegativity difference between bromine and oxygen. Maybe even the negative charge on oxygen as well. So I'm just going to also put or the negative oxygen. See if I can kind of fit it at the bottom. So I'll just circle this as well. This can also be the main attractive force. Okay, so let's see what the junior tutor said. The Lewis dot structure is a representation of an atom, ion, or compound that shows how the valence electrons of the atoms are distributed as bonds, lone pairs, and sometimes radicals. To draw the Lewis structure, first we must identify the central atom, and in this case, bromine is likely to be the central atom since it can exhibit an expanded octet and thus create more bonds than oxygen. With this, we can draw the following skeletal structure. Okay, so they showed their skeletal structure, and they have their final Lewis structure, which has the negatively charged oxygen and the two double bonded oxygens as well. So for part B, electron groups refer to the bonding groups and non-bonding groups, lone pairs and or radicals. On the Lewis structure drawn, bromine has 4 electron groups, so 3 bonding groups and 1 lone pair. And they have a Vesper table that summarizes each of the different shapes corresponding to each hybridization. So here, since we have the 1 lone pair and we have 4 electron groups, this is a trigonal pyramid molecular shape. And the electron geometry is tetrahedral. For part D, yep, they said trigonal pyramid. And for the polarity of a molecule, this depends on the presence of a net dipole moment. Each bromine-oxygen bond is polar. Additionally, the shape of the molecule prevents the dipole moment from each bromine-oxygen bond from totally canceling out. Thus, the molecule contains a net dipole moment, rendering it to be polar. And then for F, there are 3 main forces of attraction. London dispersion forces, dipole-dipole, and hydrogen bonding. The first one, the London dispersion force, is present in all molecules, but is a weak force of attraction. The second can happen between two polar molecules. Lastly, hydrogen bonding also occurs between polar molecules, but specifically to those that have polar hydrogen fluorine, hydrogen oxygen, or hydrogen nitrogen bonds. So based on these, the major or strongest attractive force is the dipole-dipole interaction. Okay, so I'll say this solution is correct. Great answer. And for the last part, I'm just going to add that the negative charge on oxygen can attract cations to form ionic bonds as well. This can be another attractive force for this ion. Yeah, so I'm not sure if they meant like intermolecular forces or intramolecular forces, so I'm just going to add that as well. But this solution is correct. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can leave it a thumbs up and comment, or share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.